Objective 8.8, Properties or Laws of Logarithms. Depending on the book that you're in, they're called both. Our book happens to call them Properties of Logarithms. There are also books that call them Laws of Logarithms. So just know that they basically mean the same thing. So we have three properties or laws of logarithms that we want to work with in today's lesson. The first one is called the product law of logarithms. And it says that for all v and w greater than 0, that if I take the log of the product of v times w, then that is the same as saying that I can take the log of the v plus the log of the w. And it doesn't matter if we're talking log or natural log. It works the same way. Now be careful that you're not thinking that this is quote-unquote distributive property, because it's not. These are not the right operations for distributive property. But it is sort of that idea where we can take this product and we can split them up by taking the log of each factor and adding those logs together. Okay, so just as a quick example, if I'm asked to expand the log of 4x, I can rewrite that as the log of the 4 plus the log of the x. These two things mean the exact same thing and will give me the exact same value if I substitute something in for x. The other thing I need to realize is that I can go either direction with this. So I can either expand expressions or I can condense them. So I may start with something that looks like the right side and I want to condense it into something that looks like the left side. So these properties and laws will work in both directions, taking something like this and expanding it, or taking something like this and condensing it. Okay, second law or property is the quotient law of logarithms. And what it says is if I take the log of some quotient like v over w, I can rewrite that as the log of v minus the log of w. Now again, these should kind of make sense because if logarithms are associated with exponents, we know that when we multiply exponents, we add the actual exponents themselves. And we know when we divide, we have to subtract the exponents. So it's all interconnected here as to how these things work. So in this case with the logarithms, the log of a quotient is the same as the log of the numerator minus the log of the denominator. And again, it doesn't matter if we're taking common log, natural log, or any other kind of log. It always works this way. So an example of this might look like expand natural log of x over 5 as a difference of natural logs. So you would rewrite it as natural log x minus natural log 5. And you always make sure you go in the order, top first, bottom second. The third law, or property, is called the power law of logarithms. And it says if I'm taking the log of something raised to a power, I can rewrite that by taking the power, the exponent, bringing it down in front of the log, and turning it into a product. So this k is being brought down in front of the logarithm, and now you're just multiplying it to the log rather than actually having it up here in the exponent. And again, same thing here with natural log. Here's my k. I'm rewriting it by bringing it down in front and making it k times the natural log of v. So an example of that might look like this. Rewrite the natural log of x cubed as a product. So my exponent in this case is the 3, and that 3 would need to come down in front so that I can write it as a product, 3 times natural log x. And again, these can go either way. This would be considered expanding, and this would be considered condensing. Okay? All right, so what if we're asked to expand an expression like the natural log of x squared times y to the 5th? Well, the first thing we can recognize is the fact that we're taking the natural log of a product, and so our product property says I can rewrite that as the natural log of x squared plus the natural log of the y to the 5th. Then I can also recognize that my x and my y have exponents on them. So now I can use the power law to actually bring the 2 and the 5 down in front of their respective logarithms. So I can ultimately end up writing this as 2 times the natural log of x plus 5 times the natural log of y. How about in the next case? I have the log of the square root of x over y. Now again, I can recognize that I'm taking a quotient, so I'm going to need to subtract. I also can recognize that the square root that is around this x can be rewritten as an exponent of 1/2. And the reason that that's helpful is because now I can use the power law and bring the 1/2 down in front of the log of x. So I end up with 1/2 times log of x minus the log of y. Okay, we can also go the other way. We can take something that is spread out and try to condense it into a more compact expression. So if I start with the natural log of 2x plus 2 times the natural log of x minus the natural log of 3y. The first thing I can recognize is that this one logarithmic expression has a number out in front of it. So that means I can rewrite it back up on the exponent, on the x, as an exponent. So I'm taking this middle expression and rewriting just that as the natural log of x squared. Now that everything is just natural logs with no coefficients out in front, now I can look at the adding and the subtracting to rewrite them as products and quotients. So the 2x from this term is going to be multiplied by the x squared in this term because of the addition, and that's going to give me the 2x cubed. And then subtracting the ln of 3y means I can make that the denominator in my quotient, so that I end up taking a single natural log here of this entire expression, 2x cubed over 3y. Okay, let's try another one. Again, first thing I can recognize is the fact that I have a number out in front of this natural log, so it can be brought up as an exponent on the x. And then inside of the parentheses here, since I'm adding, I can multiply the x squared with the x, which will give me an x cubed. Now, because I'm subtracting these two natural logs, I can rewrite that as a quotient, which would be x squared over x cubed, but then I can simplify that and make it the natural log of 1 over x. Okay, so why don't you give a couple a try? We have one problem where you need to expand the expression, and one problem where you're trying to condense it. Stop the video for a moment while you try these out and come back when you're ready to check your answer. Alright, so in the first expression, we have the natural log of x squared over y. That's a quotient, so we can subtract. We also have this x squared, and so the 2 can come down in front of that first natural log term. So 2 natural log x minus natural log y would be your expanded expression. Going the opposite way, I had 2 log x plus log y minus 3 log x to start with. The 2 and the 3 that are coefficients out in front can be rewritten as exponents. And then taking x squared times y gives me my numerator. And then divided by, because of the minus, divided by the x cubed gives me my denominator. And then again, I can simplify things to end up with the log of y over x. All right, well, not only can we use these properties with variable expressions, we can also use them with actual numbers. Sometimes you don't have a calculator available in order to figure out what a logarithm is actually equal to, but you are given some values that you can use. Okay, so here's an example of that. We're given 4 different values that we can use. We're being told that the log of 7 is approximately 0.8451, that the log of 3 is approximately 0.4771, that the log of 5 is approximately 0.6990, and the log of 2 is approximately 0.3010. So how do I use that to figure out what the log of 12 is? Well, our goal is to try to rewrite 12 in some way using 7, 3, 5, and or 2. So it's kind of like those games that we played in class where you have to use certain numbers to get other numbers. You can only use, in this case, 7, 3, 5, and 2 as a way to come up with the number 12. Okay? And so one possibility might be to take 3 times 2 squared. Okay, I know what the log of 3 is, I know what the log of 2 is, and if I work this out, I know any exponents are just going to come down as numbers to multiply. So I'm going to rewrite 12 as 3 times 2 squared, and then I'm going to use the properties to expand this so I can then substitute the values in place of the logarithms. So the 3 times the 2 squared means I can split it up with addition. And then the 2 squared means I can take the exponent and bring it down in front. So I end up with the log of 3 plus 2 times the log of 2. And now I just have to take the values for log of 3 and log of 2 and substitute them in. So 0.4771 plus 2 times 0.3010 ends up being equal to 1.0791. And if you actually went to a calculator to check that, you should get an answer that's pretty close to that. How about the next one? We've got the log of 0.6. How do I make 0.6 out of 7, 3, 5, and 2? Well, one possibility is to change the 0.6 as a decimal into 6/10 as a fraction. Because as 6/10 in fraction form, we can then see that that would be simplified to 3/5. And once I change it to 3/5, now I'm dealing with logs that I have values for. So now I can rewrite the log of 3/5 as the log of 3 minus the log of 5. Now I substitute in the values for those logs, and I end up with the log of 0.6 being equal to negative 0.2219. All right, so using those same four values, go ahead and try to come up with the answer for the log of 63. Pause the video for a moment while you work it out and come back when you're ready to check. All right, so one possible way of rewriting 63 would be to take 7 times 3 squared. And if I do that, then I can use properties to split them up and to bring the 2 as the exponent down in front. So I end up with the log of 7 plus 2 times the log of 3. Now I can substitute the values in from the list that I was given, and I end up with an answer of 1.7993. All right, last type of problem for this objective is what's called a change of base formula. And this can be handy when you're trying to actually get a numerical approximation for a log, but you're using a base, something other than 10 or e. And therefore there's no button on your calculator to get that answer. So for example, in particular, I guess this is just a little caveat here. So in particular, if I want to go with the log base c of u, one way I can get it is to take common log u divided by common log of c. Okay, this is on my calculator. Common logs are a button on my calculator. So are natural logs. And so what the change of base formula allows you to do is it allows you to find the logarithm of something that has a base that's not on your calculator by using bases that are. Okay, and so it's always going to be the log of this number first, and then divide that by the log of whatever your base was. So now let's take a look at an example. Use the change of base formula to rewrite the expression. Then use a calculator to evaluate the expression and round your result to 3 decimal places if necessary. So if I want to know the log base 3 of 7, you can look and look and look and look. But on most calculators, you are never going to find a log base 3 key. So instead, we can use the change of base formula to rewrite it as the log of the 7 and then divide it by the log of the 3. So now we're dealing with this in logs that are base 10 rather than logs that are base 3. Change of base. And because I chose base 10, I have buttons on my calculator for that. So I hit log 7, divide it by the log of 3, and I get approximately 1.771. I could do the same thing with natural logs. So let's try that on the next one. If I want to find the log base 5 of 16, again, I'm never going to find a log base 5 key on my calculator. So one choice is to take natural log of the 16 divided by the natural log of the 5. I'm changing the base from a 5 to an e by using natural log. And if I work this out, I end up with about 1.723. So it doesn't matter whether you use logs or natural logs. Just choose one or the other because those are the buttons you have on your calculator. All right, so last example. Go ahead and try to change this into a base that you can use on your calculator so that you can find the actual value of this expression. Pause the video for a moment if you need to, and come back when you're ready to check. All right, so if you chose log as your new base, then you would end up with the log of 15 divided by the log of 5, and that should give you approximately 1.683. If you decided to use natural log, then the natural log of 15 divided by the natural log of 5 would also give you about 1.683. So either way, you're going to get the same answer. All right, that should be the information you need to be able to work on your 8.8 practice. Please make sure that you're asking questions in class if any of this is still a little confusing to you, or go back and rewatch it again on the video, whatever works better for you. When you're finished with this objective, make sure you get it checked off of your list by Mrs. Gordon, and then we're ready to prepare for the second quiz in this chapter, quiz 8B, which will cover the objectives we've been talking about in objectives 8.6 through 8.8. We'll see you next class to keep working on chapter 8.